Our unit learning objectives for this unit include, I want you to be able to explain what a correlation does and why you cannot determine causality using a correlation. I also want you to be able to identify when you're going to use a Pearson product moment correlation. I want you to be able to write the research and null hypotheses and symbols and words correctly. I want you to be able to test the assumptions to make sure that you know that you can calculate a Pearson product moment correlation. I want you to be able to find the correct critical values for the Pearson product moment correlation. And then I want you to be able to make a decision about your null hypothesis for the Pearson product moment correlation using the hypothesis testing steps. And then I want you to be able to interpret the strength of a Pearson product moment correlation. And then I want you to be able to conduct any relevant follow-up analyses for it if you have significant results. All right, let's go ahead and get started. So I had this posted on Facebook a long time ago, and I said, does anyone have a favorite article of how a correlation was misapplied? I'm trying to find a really good example of how correlational research is abused. And one of my friends put, I believe you're referring to the entire internet. And I kind of laughed because that's really, really true. And if you're going to move on to the research methods class in the fall with me or one of the other research courses that some people have to take, this is something that you're going to really need to keep in mind. That correlation does not equal causation, because people make this mistake all the time. It's really, really frustrating for people who know what they know about correlation. So let's get into that so you all can be in the know also. Introduction. Where have you heard the word correlation being used? So I know we're not here in class, but y'all can type in the comments of where have you heard the word correlation being used before? A lot of times when we get into a research methods class after we're out of the statistics course, students will be like, these items are correlated, just trying to use the word and mean related. But then they kind of use it wrong, because when we're talking about research, correlation has a very specific meaning. It means that you ran a correlation like we're learning in this unit. So the Pearson product moment correlation is the one that I'm going to teach you. There are definitely other ones that you would use. There's one called a Spearman rank order correlation that you would use with ordinal data, but we won't cover that one in this class very much. All right, so you hear it on the radio if you still use it. There's television shows that talk about it, newspapers if they still exist. You see them on Facebook, you see them everywhere. Podcasts probably talk about them now. I could update my slide to say podcast or something like that, but you hear them everywhere. And for example, if you see, I have this article where it says how coffee can help you live longer. And actually, that is a misnomer. That's not right, because when you go and look at the study, it's actually a correlational design. And so basically what a correlation does, at least what the Pearson product moment correlation does, is we take two variables that are measured on a scale that come from the same people, so the same participants, and we see how related those two items are. So in order to determine cause and effect, you actually have to do a different type of design. You'd have to do something they call a true experiment, and that's where they take all their participants, so let's say we have 100 participants, and then they would randomly assign participants to be in two conditions. So we'd have the placebo condition versus the treatment condition, and then we'd see if there's significant differences in the dependent variable between the two groups. Now with the correlation, we're actually using the same people. We're just looking to see if there's a relationship. We can't determine causation at all from a correlation. So again, a correlation looks to see how strongly two variables are related to one another. Just because two variables are related to one another does not necessarily mean that one causes another. So in other words, you're going to hear me say this 100 trillion billion times. Correlation does not equal causation. I used to joke that if you got this wrong on the final, then you should not graduate from my course. You should retake it, do not pass go, and collect $100 and come right back in the fall to statistics. This year's a little bit different in that you guys are getting this lecture via online video, but I hope that you take the time and you make sure that you watch this video all the way through and you really keep it in your brain that correlation does not equal causation. And so a lot of times when I get into the research methods course, students will want to do research on abuse and what causes abuse. And I always tell students you can't do that, right? You can't do a cause and effect study with abuse, because in order to do that, you need to take a whole big sample of people. You'd have to randomly assign them to conditions. And in one condition, you would give them all the things that you thought caused abuse. And then the other group, you would have to keep the placebo group free from all of those things and then see which group had higher rates of being abused. And it's not ethical. You can't do that. Or people want to know what are some of the effects of abuse. And that's the same thing. We would literally have to take a sample of people, randomly assign participants to be in one of two conditions. In one condition, we would abuse those people. And then the placebo group, we would make sure those people were not abused. And then we'd have to see what differences there were between the two groups. That's not ethical. We can't do that. And I'm not insinuating we should do that. But it's important that when we keep in mind when we're looking at differences between people who have been abused and people who have not been abused, those are pre-existing groups. So we can't find causation using that. All right. So for example, if we found that there was a significant correlation between the number of donuts the students in our class ate over the last year and the number of time the students in our class went to the zoo over the last year, there's a number of things that could be happening there, right? So one possibility could be that the number of donuts you ate last year caused you to go to the zoo a certain number of times, right? Another possibility could be the number of times you went to the zoo last year caused you to eat a certain number of donuts last year. A third possibility, though, is something else, like having children, impacted the number of donuts you consumed and the number of times you went to the zoo last year. When we do a correlation, we don't know which one of those possibilities it is. And it actually could be a fourth possibility as well, that there's actually no real relationship between the number of times you ate the donuts and the number of times you went to the zoo last year. It was just a fluke. And that fluke is called a spurious correlation, which means it just happened that they were related to one another. We'll talk about that in a further slide in a little bit. But the big thing to look at is when we're doing this correlation, you don't know which one of these possibilities it is. It could be any of these four, right? One of the items could have caused another item could have caused the other. Something else could have caused both of them to fluctuate in their scores, or it could have just been a random mistake. It could be a spurious correlation. And so this is something that confuses students a lot. A lot of times students will realize they can't say cause and effect with the correlation. And then what they end up doing when they get in the research methods class is finding all the different words that could mean cause and effect and try to put that in instead. And then I have to keep bringing them back that correlation does not equal causation. Okay, so repeat with me. Correlation does not equal causation. Correlation does not equal causation. So again, however, from a correlation, we cannot, let me repeat again, we cannot tell what caused what. We just know there's a relationship there if it has a significant correlation. So again, correlation does not equal causation. Even with me saying this, even if you watch this, I'm still going to have students that will miss this on the final exam or will not understand this. So I will keep repeating it over and over and over again, and hopefully you will have said it out loud yourself. So hopefully it'll stick in your brain. All right, so for example, there is actually a correlation between the number of people who have drowned by falling into a pool and the number of films that Nicolas Cage appeared in during the same year. So if you follow this, there's actually a relationship between those. That is a spurious correlation. I know sometimes people make jokes about this, some distasteful jokes about it, but what we see here is that just those numbers just happen to coincide with one another, right? They don't cause one another. So why are variables related? And we kind of looked at this with the donut example. There's many reasons variables can be related. Variable A may cause variable B, okay? Or you might have variable B causing variable A. Something else could cause both variable A and variable B either to go up or go down. And then again, with spurious correlation, there really isn't a relationship between variable A and B. The relationship shown in the numbers is random, like our Nicolas Cage example that we just did. This is also known as a spurious correlation. I mean, come on, Miss Americas, come on. So murders by steam, hot vapor, and hot objects is correlated with the age of Miss America. They don't cause each other. So yeah, don't at me. They don't cause each other. So it just happens to be a spurious correlation. Just happens to be a random relationship where a correlation does exist. Okay, so like I said, these levels of measurement are going to come back and haunt us over and over again. So correlations are a little bit different. This is a different type of analysis than we've seen before because we don't necessarily have independent and dependent variables with correlation. So when we're doing this, we're literally just going to look and see how two variables relate to one another. The simplest and most common type of correlation is the one that we're going to do, and it's called the Pearson product moment correlation. It's also called the Pearson's R, so sometimes that's what you'll hear it called. The other type that I mentioned previously in the slides was that there's one called a Spearman's row or Spearman's rank order correlation. And this is basically looking to see if there's relationships between data that's on an ordinal level of measurement. So the Pearson product moment correlation, this is the statistical analysis where we examine the linear relationship between two variables that are measured on a scale. What's a scale again? I'm Dora exploring you. So I'll ask you a question. You shout it out at your computer while you're doing this lecture in your leisure. So what is a scale? If you said interval or ratio level of measurement, you're correct. So here, what we're going to have is we're going to have two variables, and both of them need to be on either an interval or ratio level of measurement so that we can do this analysis. If not, then you have to do something else. Okay, so when we have correlations, we can have positive correlations and negative correlations. A positive correlation is also called a direct correlation. You'll hear people switch between these two. They mean the exact same thing. So when we have a positive correlation, high scores on our first variable are generally paired with a high score on the second variable. So they both go up. Okay. It also may mean that a low score on your first variable is paired with a low score on your second variable. So if we were to plot a scattergram, so a scattergram is basically a display of visual data where we find the pairs, our X and Y pairs. So when we do a correlation, our first variable we typically will call variable X. Our second variable we'll typically call variable Y. So this is kind of new because in the past we just had X's that we were dealing with. So each X and Y score comes from the same participant. So for example, if I wanted to do a study and see if there's a significant relationship between the number of minutes I play Pokemon Go and the number of minutes I'm walking, I would have variable A would be the number of minutes that I'm playing Pokemon Go, and variable X would be the number of minutes I'm on Pokemon Go. Variable Y would be the number of minutes I'm walking, right? And so when we do a scattergram, what we do is we have basically, it looks similar to how we set up our histogram, but we have variable X on the X-axis, the variable Y on the Y-axis. And what we do is we find and place our points for each individual score. So if I play 20 minutes on Pokemon Go and I walked 20 minutes yesterday, I would look along the X-axis where 20 minutes are and then intersect that with where 20 minutes of walking are, and I'd put a dot there. And that would represent me as a participant where my point is. And so if we were to plot all that out on a scattergram where all of our X and Y pairs intersect for every single participant in our sample, the slope of the line would go from the lower left-hand corner to the upper right-hand corner. All right. So for example, if we found there was a significant direct relationship between the number of hours of studying statistics and the grades on your statistics final exam, what would that mean? So I'm doing that Dora Explorer thing again. What would that mean? Pause me, yell it out loud so you can practice like we're in class. This would mean that across multiple participants, that the more hours people spent studying, often the higher grade they got on the statistics exam. This does not mean that studying caused the participants to do better on the exam. This just means that there's a relationship, right? So we don't know if the study, so if we were looking at the four possibilities, right? One possibility could be that the more time spent studying did increase the score, or increased test scores caused people to study more. Or a third option could be that a third variable increased both at the same time. So for example, maybe being a responsible student is actually what caused you to do better on the exam. That means coming to class every single time, coming on time, doing every single reading, spending time studying throughout the whole time instead of at the end. So there may be a whole bunch of different variables that come into play, but we don't know from the correlation. The fourth possibility that there's not actually a relationship, that these things just happen to relate to one another, but it was more by a mistake or a spurious correlation. But we can say with the correlation that these things are related. So Another type of correlation that we could possibly get when we calculate our Pearson's R would be a negative correlation. So another way of calling, or another name for the negative correlation, is an indirect correlation. Okay, so this means that high scores on the first variable are generally paired with low scores on the second variable. It's kind of like this. This one's really confusing for students sometimes because it takes some getting used to. So if we look at a visual display of data, so the scattergram, like I told you before, where we plotted the intersection of the points of x and y variables, the slope of the line would be from the upper left-hand corner to the lower right-hand corner. So if you remember slope, when we're talking about slope, we're talking about the slope of a line, like y'all learned in previous math classes. So for example, if we found that there was an indirect relationship between the number of hours of watching Netflix and the grade on your statistics final exam, what would that mean? So take a minute, pause me, think about what we're saying here with relation to what this slide said. Go ahead and pause me, digest the information, answer it out loud to yourself, and then go ahead and keep moving on in the presentation. Okay, so what this would mean is that across multiple participants, the more hours people spent watching Netflix, so the more that the hours went up, the lower the grade they got on their statistics exam. So that would be an indirect correlation or indirect relationship. And so if we calculate our test statistic and it comes out negative, that's what it's saying, is that we have an indirect correlation. And sometimes you would expect this to happen, and sometimes you wouldn't. All right, so this does not mean, however, that watching Netflix caused students to do worse on the exam. It just means there's an indirect relationship. In order to determine causality, we would have to do some sort of true experiment where we randomly assign people to spend a certain number of hours watching Netflix and then keeping the other condition from watching any Netflix and seeing who did better on the test. That's how we would determine causality. What type of analysis would we use to do that? So for that example, we would use an independent samples t-test, which we've already done. So we cannot find causation with the correlation. So indirect correlation, an example that I saw out in the real world was the prevalence of depression among adults decreased as family income levels increased. So what they're saying with this example is that as family income went up, depression levels went down. That's only to a certain point. Where certain needs are being met. But that was definitely an indirect correlation that's out there. And I have a data brief from the Centers for Disease Control for that reference, if you're interested. So the strength of the correlation. So this gets really confusing because how strong or how related our variables are does not depend on whether it's positive or negative. What it depends on is actually the size of the correlation. So let's talk about that a little bit. So correlation is bounded from -1 to +1. Those are fancy words that one of my professors used in grad school for the correlation. I had no idea what it meant, so I'm using it here so I can explain it to you in case somebody says that to you at a later time if you go on to another stats class or research class. So what this means is that the smallest number that a correlation can be is -1.00. The maximum number of a correlation is 1.00. So if I were to say I had a correlation of 5, what should you say to me? So you guys are in your homes, hopefully, so you probably can yell anything you want. You say, "You're a liar, Jacobs, you're a liar." Yeah, because it can only range, the range for a correlation is only from -1 to +1. That's it. All right, so the closer that a correlation gets to -1 or to +1, the stronger the correlation is. Okay, in a correlation, the positive and negative symbols only tell us whether the correlation is a direct correlation or an indirect correlation. So if our correlation is positive, that means it's a direct correlation. If our test statistic is a negative value, that means it's an indirect correlation. Okay, so correlation of 0 means there's absolutely no relationship between the variables at all. Absolutely none. So the closer we get away from 0, or the further away we get from 0 towards the -1 or the +1, the stronger that correlation is. So the strength of the correlation is found in its magnitude. And so that means if we were comparing a negative correlation to a positive correlation, an easy way to be able to see which one was stronger is you could literally take the absolute value of both of them to see which number is bigger. That would make it easier for you if the negative numbers are kind of confusing. But hopefully you'll be able to just automatically look at it and be like, okay, this one's closer to -1 than that one is to +1, and be able to decide which one was larger. So let's do an example to practice that, right? So it's easy to talk about, but sometimes it's a little confusing to understand. So which one is stronger? Which correlation is stronger here? -0.77 or 0.33? Go ahead and answer this out loud right now. If you're in public, you can just say it in your head. So pause me and answer right now. Okay, so if you said -0.77 is the stronger correlation, you're correct. Remember, the positive and negative signs only tell you whether there's a direct or indirect correlation. It tells you nothing about the size of the correlation. So the scattergram, you heard me kind of pre-shadow what a scattergram is. So let's get into that a little bit. So this is one way to get a visual of the data that you're examining, what the Pearsons are. Sometimes you'll hear a scattergram called a scatter plot, scatter diagram. They all mean the same thing. So when we did our histogram unit, I went in and said that, hey, we do have another visual display of data that we'll do later on. It's called scattergram, and this is it. We are here. We have arrived. So again, the scattergram has a lot of different names, including scatter plot and scatter diagram. I don't know why statisticians like to call things a million different names, but they tend to do that. The scattergram is a visual representation of a correlation. So it gives you an idea what it looks like, which is really important because typically in order to do a Pearson product moment correlation, you want there to be a linear relationship. And so when we go to look at our assumptions, that's one of the assumptions that we're going to end up checking. And in order to test that assumption, you have to make your own scattergram. Okay. So to create the scattergram, you'll find the intersection of the X and Y for each participant and put a dot on the graph. You use the scattergram, again, to check your data, make sure that there's a linear relationship before trying to analyze it with the Pearson product moment correlation. Okay. Pro tip, use a pencil when you're doing this. This is the same tip that I gave you all when we were doing our histograms and our frequency distribution tables, our ungrouped frequency distribution table, our cumulative frequency distribution table, our grouped frequency distribution table. If you use a pencil, it's going to make it a lot easier, especially because you may have two participants that have the same variables or the same numbers for the variables. And if that happens, you actually have to erase and put a number there. So we'll get to that in a minute, though. Okay, so creating your scattergram. First step is you're going to designate one variable as X and the other as Y. Step 2, you're going to draw the axes about equal length for your graph. Step 3, you're going to place the high values of X to the right on the horizontal of the axis and the high values of Y toward the top of the vertical axis. So if we remember back from our histogram unit, what value is where our X and Y axis meet? What value is that corner unless we say otherwise? You're right, it's a 0. And so as we move away from the 0, the numbers get larger. So step 4, for each pair of scores, you're going to find the point of the intersection for the X and Y values and indicate it with a dot. Where the dots exactly overlap, you're going to substitute them for the integer telling how many cases occurred in that spot. So if you have 3 participants that have the same exact values for X and Y, you wouldn't have a dot there. You'd put the number 3 there instead. Okay. Step 5, you're going to name each of your axes, and then you're going to give your entire scattergram a name. So here's an example. So if we look at it closely, I have an arrow pointing toward one of the dots, and that's the point where X and Y pair together. So if you see from it, the attitude and number correct scatter plot. So I can't read it because the font's so tiny, but I think the X-axis says the total number of problems correct out of 20. And then the Y-axis is attitude toward test taking out of a possible 100. And so what we did is we looked at that for all of our participants. So both variables were answered by each individual participant. And then then we found where those points intersected on our scattergram. If you have any questions, feel free to ask in the comments. Comments aren't required for this perusal assignment, but if you have them, please let me know. Okay, so determining linear relationships with scatter plots. So after you have all your little dots plotted on there, you want to look at it, okay? And you want to look and see if you were to draw a line through all of your dots that you have on your scattergram, what would that relationship look like? So if we look in our first little visual depiction here on the slide, we see that that one's showing a linear relationship that looks like a direct relationship. So and this is one of the reasons why I have you all make sure that you're doing your hypothesis testing steps in order, because when you make your hypotheses, you want to do that before looking at your scattergram, because if you look at your scattergram, then you're going to have an idea whether it's direct or indirect relationship, and that's not an ethical thing to do because we need to make our hypotheses before we're looking at our data to keep us honest. Okay, so we look at the second scattergram there on the slide, we see that that's also a linear relationship, and that one looks like a indirect or an indirect relationship or a negative, because what we see is as the X values go up, our Y values go down. And then what we have on the last two scattergrams are relationships that aren't linear. The first one that we see there is called curvy linear relationship. And that's where there's kind of an arc. There's not a straight line that best fits our data. And so you could not, if we go in and we get to the assumptions and we look at that scattergram, we would not be able to do a Pearson product moment correlation on that data because we would violate that assumption. And then we look at the nonlinear relationship, the last one, and that's a kind of a upside down U-shape relationship, and we would not be able to do a Pearson product moment correlation with that data either. There was once, when I was in grad school, one of our professors talked about how they chaired some sort of dissertation or something like that, and they were looking at reading level and something, and what they found for their dissertation was that reading level was not necessarily linear. We didn't always just straight go in a line with our reading level going up as we increased in grade, and they ended up winning this huge dissertation award, which should have not been a problem because all these scientists should have been checking these assumptions. This is one of the reasons why I hound these assumptions in so much for you all, is because we really need to be checking them to see if we're using the proper analysis. And this is one of those that they didn't check in that entire field of research. So that means all of those studies that had been done that didn't check this assumption were probably not valid. And they should have actually used some other type of analysis to examine their data set. And that's huge. And that's really problematic because we have policies, we have laws, there's so many things that are based off of research that could actually harm people if it's not done correctly. Okay, so the correlation and the hypothesis testing steps. When we're testing our correlation, we're actually seeing if our correlation is significantly different from zero. Why would we do that? So pause me, think about it for a minute before moving on. Don't just let this video play or you're not going to be ready for the exam over this, okay? So why would we test to see if our correlation is significantly different from zero? Okay, so up to this point, we've been just seeing if there's been significant difference between groups. So with our one sample Z test, we wanted to see if our sample mean was significantly different from our population mean. With our independent samples T test, we wanted to see if there were significant differences in the means of two groups made up of different participants. With the correlation here, it's a little bit different because what we're trying to see is if our correlation is significantly different from zero. What does a correlation of zero mean again? A correlation of zero means there's absolutely no relationship. So when we're testing with the hypothesis testing steps, what we're trying to see is our correlation far enough away from zero that there's a relationship that didn't occur by chance. So note here, I'm just saying, does this relationship not occur due to chance? I'm not saying anything about how meaningful or how strong that correlation is. We would find that out later in some follow-up analyses if we needed to. All right. So this is a little bit different. We're still going to label our normal curve the same way because the zero will be directly in the middle. We'll have a different critical value table for this, and we'll talk about that when we get there. But our 0 or our correlation of 0 or R equals 0 will be in the middle, right? And then we're going to see where our test statistic falls and if it's far enough away from 0 that that correlation didn't happen by chance. So our hypothesis testing steps, hopefully you have this memorized by now. Let's go through. I'm going to ask you what they are. Test yourself. Nobody else is around, so no one's judging you. Go ahead and try to test yourself. What's our first step? So the first step in the hypothesis testing steps, no matter which analysis we're doing, is trying to figure out which statistical analysis you're going to run. So what's our second step? What do we do next? If you said we write out our research and null hypotheses in symbols and words, you are correct. You got it. What's our step 3? Step 3 is checking those pesky assumptions to see if we can run our analysis or not. Then what is step 4? Step 4 is calculating our test statistic. Here we're going to be calculating Pearson's R, which will be symbolized by lowercase italicized r. Step 5, what's that? So step 5 is finding the corresponding critical value or values. And then step 6, what's step 6? You're right, we're going to make our decision about our null hypothesis. Remember, whenever we're making that decision, it's always with relation to our null hypothesis, and that we will need to write our decision out in words, but also in symbols. Okay, our 7th step then is conducting any relevant follow-up analyses, and we'll talk about that when we get there. All right, so step 1, determine which statistical analysis you're going to run. What is the purpose of the analysis? So we remember there's certain questions that we're going to ask ourselves to determine what analysis we're doing. Up to this point, we've just been finding differences. This is where this shifts a little bit, because with the correlation, our purpose of this is to see if there's a significant relationship, what combines them together between two variables that are each on a scale. So both of our variables must be on an interval or ratio level of measurement. Again, instead of having dependent and independent variables with the Pearson product moment correlation, we have at least just two variables that are on a scale. They are not independent or dependent variables. They're just plain variables out there. All right. The data for the two different variables will become from the same participants. Okay. So if we wanted to see if there's a relationship between the number of tattoos somebody has and the number of times they've been arrested, we'd literally go through and ask each of our participants, how many times have you been arrested? And how many tattoos do you have? And then we take that data to see if there's a relationship between the two. So for example, we could examine the correlation between the number of street tacos you had in last week and your level of happiness, right? So I had 0 street tacos last week, so I'm very sad. No, I'm joking, right? Because we know correlation does not mean causation. All right, step 2, then we're going to write our research and null hypotheses in symbols and words. We're pros at this by now. We're just going to have a new symbol that you're going to put. So for correlation hypothesis, again, when testing the hypotheses for correlation, we're trying to see if the correlation that we calculate is statistically significant from 0. So how do you think we might write our hypotheses then? What would our first symbol be for our research hypothesis? If you said H sub 1, you're correct, right? So we'd have H sub 1, we'd have our colon. What would be next? So if you said we probably would put our symbol for correlation, that's 100% correct. And then you have to determine whether or not you're just looking for a significant correlation, so a non-directional test, or if you're looking specifically for a direct or an indirect correlation, because that would change what symbol you put next, okay? And then you'd put 0, because we're trying to see if our correlation is significantly different from 0, okay? So again, why would we want to test to see if our test statistic is significantly different from 0? Because if our correlation equals 0, then it means there's no correlation. Our variables are not related at all. And we went through that a little bit earlier. Okay, so this is what our research hypotheses look like. So the symbol for the correlation of a sample is R. So lowercase italicized R. Go ahead and put that on your handy dandy symbol sheet if you didn't do it earlier when I first introduced it to you. Something else that's a little bit different is that when we're doing a correlation and we're doing it between two variables, we'll use a sub X and a sub Y to indicate that we're looking at the correlation between X and Y. All right. So if we're doing a non-directional hypothesis, if we're just seeing if there's a significant correlation, we would be conducting a two-tailed test, and we'd have H sub 1 colon, a lowercase italicized r sub xy does not equal 0. So here we're looking at the correlation between variable x and variable y is significantly different from 0. So that last part there is a template for it. So would you just write the template the way that I have it right here? No, you wouldn't. You would adapt it to whatever you're looking at. So if we go back to my example earlier about tattoos and the number of times you're arrested, a research hypothesis could be research hypothesis colon the correlation between the number of tattoos a person has and the number of times that they've been arrested is significantly different from 0. Okay, so you got to adapt that template to whatever study that you're trying to do. So then our null hypothesis, remember, is the exact opposite of our research hypothesis. The template I have here is just a template. You'll have to adapt it for a real world problem. If we had a real world problem, then we'd probably have information, or we would have information about what variable x is and variable y were, and then we'd incorporate that into the written words. So if we're going to write in symbols, we'd have h sub 0, which is our symbol for null hypothesis. We put a colon to show that we're going to do a correlation. So you could either put r equals 0 or r sub xy equals 0. Both of those formats are accepted in statistics. And then we go and write our null hypothesis in words. So null hypothesis, the correlation between variable x and variable y are equal to 0. Okay. So for example, we could say the null hypothesis for our previous example was that null hypothesis, the correlation between the number of tattoos somebody has and the number of times they've been arrested are equal to 0. Or another way that you could phrase that, because you remember I said there's tons of different ways that you could phrase these hypotheses. You could say the correlation, or there is not a significant correlation between the number of tattoos someone has and the number of times they've been arrested. So you can kind of finagle it so it fits how you would speak for your own words. So then we can also do directional hypotheses, right? And so I kind of put this on one slide so that I could show you what this would look like. So for a positive or direct correlation, you're going to hypothesize that your correlation is significantly greater than 0 for your research hypothesis. So if you see there, we have h sub 1, we have a colon, r sub xy is greater than 0. So there we're hypothesizing that we have a positive correlation. So when we go and actually calculate our test statistic, a positive correlation would be a positive test statistic value that we calculate. So then our null hypothesis, if we remember, is the complete opposite, covers every other option that our research hypothesis didn't cover. And we'd have h sub 0 colon r sub xy is less than or equal to 0. So we see here, we remember that whenever we're writing our hypotheses directionally, that our research hypothesis will either have the greater than symbol or it will have the less than symbol. And then our null hypothesis will have the less than or equal to symbol or the greater than or equal to symbol. Students still will miss that part with the equal sign for the null hypothesis. And that's because our null hypothesis has to cover every single option out there, okay? So then if we move on to our negative or indirect correlation, we would be hypothesizing that we're going to get a negative test statistic value for our correlation. And here we have h sub 1 colon lowercase italicized r sub xy is less than 0, right? Because we're saying that we think we have a significantly indirect correlation. So then our null hypothesis, then it covers every other option that our research hypothesis doesn't. So here we have h sub 0, we're going to have a colon. The correlation between x and y is greater than or equal to 0. All right. And then you would just go ahead and translate those into words. We've done it enough, I think, that you would be able to do it on your own at this point. If you have any questions, please feel free to write them in the comments if you do. Step 3, then we're going to move on and check the assumptions to make sure that we can run this analysis, okay? So our first assumption that we're going to check is that both of our variables are measured on a scale, okay? Very first thing. If both variables are not measured on a scale, then we cannot do the Pearson product moment correlation. The Pearson product moment correlation is not robust to the violation of this assumption. This is a deal breaker. So you have to have both variables measured on a scale, or you have to do something else. Okay. Again, this means if both variables are not measured on a ratio or interval level of measurement, then we cannot do the Pearson product moment correlation. You would have to do something else. Now, if the variables were both ordinal, or if you had one ordinal and one scale variable, then you could do a Spearman rank order correlation. So for example, before I've done a Spearman rank order correlation where I wanted to see if the order that people turned in their test was related to the rank of how well they did on the test in comparison to their peers. So what I did is when students turned in handwritten tests, I know, right? Super risky living back then. I would write like 1, 2, 3 in the order that they turned them in. I'd flip them over, and then I'd put it into like an Excel file so that I would have the data for each student. And then after, I would go and score their tests, and then I'd put those tests in rank order. So who did first, best, second, third, fourth, all the way through the bottom. And what I found when I did a Spearman rank order correlation is that there was no relationship between the order that someone turns in their test and how well they do on it, which I found really interesting. So long story short, if you're in a face-to-face class and you start getting nervous because people are turning their test in early and your last one, don't be nervous. There's no relationship between when you turn your test in and how well you're going to do. Okay. Assumption, the same participants are tested on both variables. So you have to have the data on both variables from the same participant for all of your participants. Okay. The Pearson product moment correlation is not robust to this violation. So that has to be true. If not, then you can't do the analysis. You'd have to do something else. So again, this means if your participants didn't fill out the information for both variables, you can't conduct this analysis. Now, if you had it for like a majority of a data set and you just had one person who didn't fill out one of the variables, what could you do instead? If you said you could just drop that participant, you're right. So if you do drop a participant, what would you also need to do when you wrote up your results? You're right. You would have to write that you removed a participant and then for what reason? And this reason would be that they didn't complete all the measures, so you couldn't do the correlation with their data. Assumption, there's a linear relationship between the two variables. So this is where you're going to go and put that scattergram information into use. So you're going to build your scattergram. If you're using some sort of statistical software, the software actually would build one for you. It's a little bit of a lengthy process. There is a really great resource called Layered Statistics, L-A-E-R-D, Layered Statistics, that has guides on how to do this in programs like SPSS, which I really like. If you don't have a very large data set, you could definitely do this by hand though. Okay, so the assumption is that there's a linear relationship between your two variables. Again, to test this assumption, you need to build a scatter plot, scattergram, scatter diagram, whatever name that you're choosing to call it. And the Pearson product moment correlation is not robust to the violation of this assumption. So that means that if you don't meet this condition, you cannot, if you don't need it, you can't do it. Okay, so you have to meet this condition. There has to be a linear relationship. It doesn't mean that your data set's going to fall straight on the line and be perfect. What it's going to mean is that your scatter of dots will tend to go in one direction. It's not going to have a really definitive U shape or really definitive curvy linear relationship with all the dots, okay? Because it will be natural that you'll see dots everywhere because there's variability in our scores in our data set. Assumption, both variables are free of significant outliers. For this assumption, you need to examine each variable individually for outliers. So how do we do that? How do we examine our data set for outliers? If you said we need to find the z-scores for each of the variables, you're 100% correct. So something to keep in mind is when you're finding the z-scores, you're going to find the z-scores for your x variable first. So you're going to do that by, what do you have to do first to find your z-score? If you said you had to find your mean first, you're right. After you find your mean, what else you got to find? So yes, you would find the mean and standard deviation for just variable x, right? And then you would use that information to calculate your z-scores for your first variable. And then you'd have to repeat that process for variable y. So you would go through, you'd find what the mean of variable y is, the standard deviation of variable y, and then you would calculate the z-score for each individual x. So if we remember, our formula for a z-score is z equals, and then it's going to be a fraction. So in the numerator, we have the individual x that we're finding the z-score for minus the mean of that variable, and then divide it by standard deviation. Okay, and then with that, we see if we have above 3.29 or below negative 3.29 for our z-scores. And if we do, then we have outliers. So the Pearson product moment correlation is robust to the violation of this assumption only if we remove the outliers and then report that in our results section about how many outliers we took out and why we took them out. Assumption is another assumption is bivariate normality. So we've seen normality before, but with our other statistical analyses that we've done, we've been looking at the normality of a dependent variable. With this, though, what we're going to be looking at is the normality of each individual variable on their own. So look and make sure that variable X's distribution is normally distributed, and then we'll also check and see if variable y's distribution is normally distributed. What do we use to check for normality of our distributions? If you said the Shapiro-Wilks test, you are 100% correct. That's what we use. And so if our p-value for the Shapiro-Wilks is 0.05 or above, then we meet the assumption. If our p-value is significant, if it's less than 0.05, then we violate this assumption. Okay, so the Pearson product moment correlation, though, good news, is robust to the violation of this assumption if our number of participants is 30 or greater. And so I think one of the students in class in an earlier session said, well, why wouldn't you always just have a minimum of 30 participants then? 100%, that's what you should do. And that's what most researchers will do, is they will make sure they have a minimum sample size so that they don't even have to worry about it. And there's many people that won't actually even test for Shapiro-Wilks test for normality when doing this, if they have a larger sample, just because every time you run a statistical analysis, you increase the chance of making a type 1 error. But that is a more sophisticated thing that we don't really need to talk about. Another assumption that we have is that the sample was randomly selected. This good old assumption that never goes away. So this just basically means we select our sample from the population of interest using random selection. What were our 3 types of sampling methods that we learned about in chapter 1 again? So if you said random selection, convenience, sampling, and snowball sampling, you are 100% correct, and that's great. So for this one, to meet this assumption, though, you had to have randomly selected your sample. You had to use random sampling. If you did not do that, you violate this assumption. Okay, so the Pearson product moment correlation, just like all the other analyses that we've learned so far, is robust to the violation of this assumption if you don't generalize your results to the overall population. Okay, so here I just have a slide that helps you check all the assumptions. So typically when I'm doing some sort of analysis, if I'm doing this in the real world, I'll literally go through these items in the specific order. So if you notice, I'm first checking the 3 that are not robust because those are deal breakers and I don't want to waste my time. After I check, so if I make sure both variables are on a scale, then I check to make sure that participants are tested on the same 2 variables. And then after I check that linear relationship, the next one I'm almost always going to check is going to be the outliers one. The reason why I like to check the outlier assumption next is because if I have to remove an outlier from my data, that changes the distribution shape. So it makes sense to do that first before going in and checking for normality, because if you have outliers and you remove them, it would change the distribution. You'd have to run that again if you hadn't. And then random sampling's last because that one likely is going to be violated, and we know it's going to be, and there's an easy fix for that. We just don't generalize outside of the sample that we have back to the population we were originally interested in studying. Step 4, then we're going to calculate the test statistics. So if we look at this formula, it's actually nothing new. So what we're looking at here is we have our correlation symbols. So lowercase italicized r telling us that we're doing some sort of correlation sub xy. So we're looking at the correlation between variable x and variable y equals. And so if we look in our numerator, what we're doing is we're seeing that we're finding the sum of the difference scores for the variable of x, and then we're also timesing that by the difference scores or the deviation scores for variable y. And then we're going to divide that by the square root of the sum of squares of x times the sum of squares of y. So if you go back and you remember when we were first learning to calculate standard deviation back in week 3, we learned how to calculate those sum of squares. So you should already have the symbol in your handy dandy symbol sheet. If not, you're going to want to go ahead and put that there now. And then you may also want to make another side note. So lowercase italicized ss sub x means the sum of squares of variable x. And you may want to add lowercase italicized ss sub y is the sum of squares of variable y. And so if you already had to go and calculate the standard deviation of each of these earlier on when you're finding your z-scores, when checking your assumptions, you literally just have to take your sum of squares for x and your sum of squares of y that you did when you're calculating your standard deviation, and you can plug it into the formula and solve this pretty quickly. Okay, step 5, then we're going to find the corresponding critical value or values. So you're going to use a Pearson's R table for this. This is a little bit different than our other table. So you'll want to write up at the top of your critical value table that it's for correlations or your R critical value table. So to do this, it's a little bit different than some of your other critical values that you found before. So when we find our degrees of freedom for our correlation, we're going to take our n, which means our number of pairs or the number of participants providing data, okay? And you're going to subtract 2, okay? And that's going to be how you find your degrees of freedom for this one. Then you're going to look at the alpha level that you set for this class. We typically just use 0.05. We would use 0.01 if we were doing a whole bunch of analyses, potentially in one study, but that is for a research methods teacher to take up with you. And then we have to determine whether or not we're doing that one-tailed or two-tailed test. So where do we find out whether we're doing one-tailed or two-tailed test? If you said we need to go back and look at our research hypothesis and our null hypothesis, you're absolutely correct. So if we wrote our hypotheses non-directionally, we're doing a two-tailed test. If we wrote our hypotheses directionally, we're doing a one-tailed test. We remember also in our critical value tables that there's no negative values in there. So if you hypothesize a negative test statistic when you wrote your research question, you would take the value, the critical value from your critical value table, and you would make the critical value negative when you were using it to find your critical value. Step 6, we're going to make that decision. In order to make our decision, we're going to go ahead and label our normal curve. So if we have a two-tailed test, we're going to have 2 critical values. They will be the same number. One will be positive, one will be negative. The only difference is when we're talking about 0 with our correlation distribution, that our 0 is actually for a correlation or a R of 0. In the middle, we have the retain the null hypothesis. And then in our 2 little tails, we have the reject the null hypothesis region. Our correlation must go beyond our critical values in order for us to reject the null hypothesis. Okay, so if we hypothesized a positive test statistic in our research hypothesis previously, then our critical value is going to be positive and it's going to be on the right side of our distribution. If we hypothesize a negative correlation or an indirect correlation, then that value would go on the left side of our normal curve. So when we write out our symbols in our results and symbols and in words, we're going to write, if we said that our correlation was significantly different from 0, so that's what we would say. We could say that we reject our null hypothesis. So if our correlation is significantly different from 0, we reject our null hypothesis, and you write it in the same format as we've written all of our other results. So you'll put the symbol for the test that we're doing. So for the Pearson's R, it's the lowercase italicized r. Then you're gonna have parentheses, and inside those parentheses, you're going to put your degrees of freedom that you calculated when you went to go find your critical value. Then you're going to have equal, and then to the test statistic that you calculated when we use the formula. You're going to put a comma. So if we have significant results, our p-value is less than our alpha level, and we'll have a 0.05. Then we'll have a comma, and then we have r squared, which is a follow-up analysis that you're going to learn in the next step, but you would put your r squared value next. And then if we did not have significant results, we would have basically the same way we've been writing them all along. We'd have a lowercase italicized r. In the parentheses, we have degrees of freedom that we calculated. We equal whatever test statistic value that we calculated using our formula, comma, lowercase italicized p equals n dot s dot, which we learned before means not significant. So there's some general interpretation guidelines for the strength of a correlation. Whenever we see a correlation of 0 to 0.20, we say there's weak or no relationship at all. So notice that when we're looking at these guidelines, that these would work for negative values as well, because when we're looking at correlations, the positive and negative value only tell us whether it's a direct or indirect correlation. So if it was negative 0.10, that would still be a weak to no relationship because it falls within that same range for the magnitude. So then a correlation of 0.20 to 0.40 means a weak relationship. 0.40 to 0.60 is a moderate relationship. Once we get to 0.60 up to 0.80, we have a strong relationship. And then once we get to 0.80 all the way up to 1, we have a very strong relationship. So whenever we have a correlation of 0, we learn that means there's no relationship at all. If we have a correlation of 1, that means they're perfectly correlated. If we drew out our scattergram, that would be when there would be all of our data points on a straight line. There would be no variability. So if we have a negative correlation, then we have the opposite, right? So we could have a -1 would mean that it's a perfectly indirect correlation or relationship. Okay, so again, remember that the strength of correlation relates to the magnitude rather than whether it is a positive or negative value. So after that, if we have statistically significant results, only if we have statistically significant results, we do step 7 and conduct any relevant follow-up analyses. So for the correlation, our follow-up analysis is going to be called coefficient of determination. And this provides a percentage of variance in one variable that is accounted for by the variance in the other variable. Note that it says accounted for. It doesn't say that it causes. It's just they're related to each other. So we talked about this a little bit when we talked about the independent samples t-test, that when we're talking about our effect size for that, is saying whatever is happening with the variation in the dependent variable occurs likely because of what group they're in. And this is kind of similar to that. So our coefficient of determination is basically where you're going to look at your correlation. You're going to square it. And that's why we have the symbol capital R squared. And so if we have a coefficient of determination equal to 0.0361, that's in proportion form, which we're familiar with now. This means about 3.61% of the shared variance is between the two variables. Okay, so again, to find our coefficient of determination, all we got to do is square the test statistic value that we found when we used our formula. And the symbol for the coefficient of determination, again, is capital R squared. You need to put that in your handy dandy symbol sheet so while you prepare for our final examination. So go ahead and do that now. You can pause me. So again, you only need to conduct this follow-up analysis if you have statistically significant results in step 6, and you would add it to your results written in symbols. So if you do not, so for example, if I gave you an assignment and you did not reject the null hypothesis in step 6, and I had a step 7, you would say, I can't do it because we didn't have significant results in step 6. The amount of unexplained variance then is called the coefficient of alienation. Okay? And so I like to end this unit with a little comic strip, which I think is funny. I used to think that correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe.